Alright, so now we're going to look at another type of problem for solving differential equations called initial value problem. The idea being, same idea, we have a differential equation to start with, but we also have one extra known piece of information, this initial value. That is when the variable is equal to 0, we actually know what the function value is. Okay, so that's our initial value, is what's the value of the function when the domain value is 0 at the start. Particularly if we're talking about t equals time, t equals 0, that's the start of whatever phenomenon we're trying to study. Right? We're going to see exponential growth functions and as one of our primary examples for the type of applications we can use differential equations for. So let's look at this one here. Remember, we just said in the previous video, if we are solving a differential equation, we want to start by rewriting the derivative in Leibniz notation. So y prime would be dy dt is our other variable here. So we have dy dt equals negative t times y. And we can use separation of variables. So we want to get all the y's on the left, all the t's on the right. So I'll divide out y. I would get 1 over y times dy dt equals negative t. I also can multiply the dt to both sides. And you can do that all in one step. You don't have to write it out separately like this. So we would get 1 over y dy equals negative t dt. What we said is, if once we get the variables separated, we want to integrate both sides to undo the derivative. To get the derivative out of our differential equation, we'll integrate both sides and then see what we have there and solve for y from there. So we want the integral of 1 over y. Well, I might rewrite that as y to the negative 1. You could do that, or you could just recognize that what's the antiderivative of 1 over y? That would be the natural log of absolute value of y. And on the right side, we have the antiderivative of negative t would be negative t squared over 2 plus a constant. Again, don't forget plus a constant when you integrate. So now I have natural log of y, and I need to solve for y. Well, how do we solve equations? Isolate the variable by performing inverse operations on both sides. So, how do I undo natural log? Hopefully we remember that natural log is the inverse of base e. Really, natural log means log base e. Log base e cancels out base e. So if we exponentiate both sides as a power of e, on the left side, the e cancels the natural log. So we'd get y equals e to the negative t squared over 2 plus c. That's all in the exponent. So now that we've solved for y, we have kind of two more things to do. I'm going to do a little bit of simplifying of this expression, rewrite that in certain ways that I think will be helpful. And we also need to account for this initial condition. So let's start by simplifying. Let's use our rules of exponents here. Let's actually bring this up. We know that when I'm adding exponents, what did I do with the bases? Right? If I multiply like bases, that means I add exponents, which means if I'm adding the exponents, I've really multiplied like bases with these two separate terms as the powers. So in other words, e to the negative t squared over 2 plus c power could be rewritten as e to the negative t squared over 2 times e to the c, using my like base property here. But e, well, remember, e is a specific numerical constant, Euler's constant. So when I say e to the c is an arbitrary constant. Arbitrary constant. So that means I really could just use c here. C is just any arbitrary constant. And e to the c would be equal to whatever constant I want it to be as well. So I can really write this as just c times e to the negative t squared over 2 power. So here is our solution to the differential equation, our general solution, but we were given a little bit extra. We were told what the initial value is when t is equal to 0. So when t equals 0, we know that y of 0, that would be equal to c times e to the negative t squared over 2 is equal to 3. So y at 0 is equal to 3, which means c times e to the, negative t squared. Well, I'm saying I could plug 0 in here, and that's all going to equal out to 3. So let's think about this for a second. That's c times e to the negative 0 squared over 2. 0 squared is 0. Negative is still 0. 0 divided by 2 is still 0. So e to the 0 power is 1, which means c is equal to 3. And if I merge that with the general solution that I found, what I found is that specific value of c for this particular initial condition, c has to equal 3. So my single solution to the differential equation would be 3 times e to the negative t squared over 2. And that is my single solution to the original differential equation that also satisfies this particular initial condition that was given over here. So there's one more type of problem that we can solve differential equations and find the initial condition. We're going to focus in on these kinds of problems when we get into the specific word problems and applications in the next couple of videos.